SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 22. In this lecture, we are going to solve some problems involving extension, torsion, inflation. Okay. So, let us begin with the first problem. So, think of a circular cylinder, but with variable cross section. Okay. And suppose that the radius here varies from r1 to r2. The cross section is circular and length, let us say, is big L, and we have applied some torque at the free end, torque T. So, the question is, what would be the rotation of the cross section at the free end? Okay. Let us say we denote it by omega. So, in the last class we talked about extension, torsion, inflation problem, and we had derived a very interesting result, that the torque T into the length L, T L by G J, that was equal to omega. Do you remember, where omega was the end to end rotation? Now, in this problem, the clamped end, there will be no rotation here, right, because it is clamped. Okay. So, that means the rotation of the other end would also be the end to end rotation, right. But the only problem is that here the radius of the cross section is varying, whereas the problem that we dealt with in the last class, the cross sectional radius was the same all along. For the entire length L, the cross sectional radius was the same. Now, recall that we also wrote this equation as torque T equal to G J times omega by L, where omega by L is actually the rate of change of rotation of the cross section, and that is also called twist. Okay. So, this omega by L we also call it as twist, and when the cross section was not varying, then this twist was constant all along the rod. But here you see the cross section is varying, that means the J, the polar moment of area, can you recall J, that was integration of small r square d A over the cross section omega naught, right. So, if you change the cross section radius, then the J, the integration of r square over the cross section will also change. So, J in this case is varying. So, in this formula J, it is varying now. So, that means the rate of change of angle will no more be constant. Okay? But we can still use this formula in this following way. We say that the torque T is equal to G j times the twist k. So, now we say this is twist. Okay. So, at a given cross section, whatever is the torque at that particular cross section, that would be equal to G times the polar moment of area of that cross section into the twist at that particular cross section. So, suppose that I am at a length x from the clamped end and we have this cross section and the torque there is T of x, then the formula would be that T of x is equal to G of x in case the material is also varying times J of x as the cross section size is changing. So, J will also be changing into the twist k of x, and k is nothing but d omega by dx now. So, instead of omega by L, because we assumed that the rate was same all along. So, d omega by dx became omega by L, but now because rate is not the same, we will simply write it as twist k of x. Okay. So, this is the formula to use now. All right. So, we have to first find out T of x, how is torque varying in the cross section. So, we can find that through free body diagram. So, let us cut this section for example. So, take this section and draw the free body diagram of this section. Okay. So, we have this beam and it has got this torque T acting here. To denote torque, we use two lines with the arrow. For forces, we use single line with an arrow. Okay. And this torque is along the axis. So, the arrow is pointing along the axis. Okay. And then over here on the other cross section, whose normal is in a different direction, right. So, if you say that this is the E1 axis, the axial direction, then this cross section has got positive normal E1, whereas this cross section has got negative normal. So, by convention on positive cross section, the torque will be pointing in the positive direction, whereas on the negative cross section, the torque would be pointing in the negative direction. So, therefore, the T of x that we will have here will be in the negative direction. So, in this direction T of x. If you take the other part of the beam, this right here the cross section, the normal is plus E1. So, it is a positive cross section. Therefore, T of x here would be pointing in the positive E1 direction. Okay. And this is also making sense from Newton's third law, action reaction pairs. So, these two are action reaction pairs. So, on the negative cross section, the torque that we have is opposite of what it should be on the positive cross section. All right. Anyway, now when we do the moment balance of this part of the beam, then the total moment has to be 0 and there is no force acting here. So, the total moment simply 0 means T, the applied torque minus T of x, that has to be equal to 0. See, the applied torque is in the positive direction, but the T of x here in the negative direction. So, we have T minus T of x equal to 0. That means, T of x is equal to T. So, in this particular case the torque does not vary as you change the cross section. So, torque is a constant here. Okay. Now, what about g of x? So, assuming that it is the same material, so g of x then becomes a constant g. If the material was changing, then g of x would be changing, okay. But here we have the same material. What about g of x? So, for g of x we have to find out what is the radius for the cross section x. So, let us denote that by a small r of x. So, we take the x cross section whose radius, outer radius is small r of x. Okay. So, j of x then by definition is integration over the cross section of r square dA, right. So, it is r square dA, which is r times dr times d theta. So, this is dA. Now, in the integrand nothing is a function of theta. So, we can do the theta integration and it will give me 2 pi. So, the theta goes from 0 to 2 pi, whereas the radius goes from 0 to little r of x, right. So, when we work out the theta integration we get 2 pi and then we have 0 to r of x r cube dr, all right, and this then becomes 2 pi over 4 into r to the power 4 and then you evaluate at the limits 0 and r of x, and finally, we have pi into r to the power 4 over 2 and this is r of x to the power 4. Okay. So, g of x we also got. So, that is your g of x. So, we can use this formula and then we get that the twist k of x is equal to T by G j, and T is constant, G is also constant, only j is changing. So, we have T by G 2 T by G pi into little r of x to the power 4. Okay. That is my twist. And what would be the final rotation then? So, the final rotation omega is then simply the integration from 0 to L k x dx, right, because k is d omega by dx. So, when you integrate this you will get omega, right. So, this means this is 0 to L 2 t over pi g 1 by small r to the power 4 dx. And now, we have to think of how is the radius x varying. So, small r at 0 is equal to small r of 1, small r at L is equal to small r of 2, and since it is varying linearly, so small r of x would then be equal to small r of 1 plus r 2 minus r 1 divided by L into x. So, that is my small r of x. So, we can come back here and say this is equal to 2 t over pi g into 0 to L 1 over r 1 plus r 2 minus r 1 by L times x to the power 4 dx. So, now it is an integration in x, you can work out the integration and get the rotation of the free end. Okay. So, I hope you got some idea about how to obtain the rotation. All right. Let us now work on the second problem. Okay, this is also an interesting problem. So, in this case we have got a shaft which is clamped at both the ends, but it is an interesting shaft. I am just going to draw it. So, this shaft is made up of 3 different shafts, and they are of different material, and they also have different cross sections, they have different length. So, suppose this is bronze, this is made up of aluminum, and this one is made up of steel. All right. The length of the bronze shaft is L b, the shear modulus of the bronze shaft is G b, okay, and the radius of the bronze shaft, that is R b. Okay. Likewise, for aluminum we have length L a, G a, R a, and for steel we have L s, G s, and R s. All right. Now, what is happening here is that we have torque acting at the intersection of bronze and the aluminum shaft. All right. So, let us denote this by T 1 and the other one by T 2. So, we have 2 torques acting of value T 1 and T 2, and they are pointing in the plus E 1 direction. All right. So, let us say this is E 1. So, both torques are pointing in the plus E 1 direction. All right. Now, what we have to find out is what is the maximum shear stress that is generated in each of the 3 components of this shaft. Okay. So, the question is what is the maximum shear component of traction on each of the 3 shafts. Okay. So, how to find this? Now, you see what we have applied to this setup is just a torque. At the clamped end where it is constrained, there is no movement, there will be some reaction torque also, is not it? Now, our goal should be to find out what is the torque in each of the 3 shafts, what is the torque that is acting in the bronze, what is the torque that is acting in aluminum, and what is the torque that is acting in steel. So, we have to find each of them, okay? And that is not easy really. See, if you solve it from pure statics, from mechanics first year thing, it is an statically indeterminate problem, which means you can't get it just by balance of force or balance of momentum. When you do balance of force and balance of moment, it is not going to give you the result. So, that is why it is called statically indeterminate problem. Okay. Let us say this end is P and this end is Q, okay. And these points here, this is big R and this is big S. All right. Let us try to draw the free body diagram of the entire shaft. So, we are going to isolate the shaft and we know that it has got this torque T1 acting in the plus E1 direction and torque T2 also acting in the plus E1 direction, and then there will be reaction torque, right. So, you look at this cross section, the cross section Q. So, the reaction torque there would be T Q, right, whereas the cross section P whose normal is negative, right, it is negative E1. So, let us suppose the torque there we denote in the negative direction with T P, all right. So, when we do the total moment balance, this tells us that T Q into E1 plus T1 plus T2 into E1 and T P is in the negative E1 direction. So, it comes with a minus sign minus T P E1, that is equal to 0, right, and this then tells us that T Q minus T P plus T1 plus T2 is equal to 0. So, we have a single equation, but two unknowns T Q and T P, and you can do force balance, it is not going to give you anything. So, basically you will have only one equation, but two unknowns. So, that is why we say it is statically indeterminate. To solve such problems, we have to take deformation into account, all right. So, as I told you, it is a torsion problem, things are twisting here, we have torque acting on the beam. So, beam is going to twist. Recall the concept from the last class. So, you have a beam and you apply some torque here. So, this means on this end the torque is like this, whereas on the other end the torque is in the other direction. So, what is going to happen due to that? If you think of a line in the cylinder, axial line, then due to the torque, that line after deformation will become helical. And depending on how much torque you are applying, it is going to twist. Let us say the torque is more, then it is going to twist even more. Okay. So, this is the deformation due to torque, or this is the torsion. Okay. Torsion. And you can recall when we are solving for the displacements u r, u theta and u z, then u r turned out to be minus of nu times epsilon z into r, plus it had something into pressure P, correct, but here we have no pressure. So, this term is not there, and we also have no epsilon z. You see it is clamped between the two ends. So, there is no epsilon z. So, this is also not there. So, here u r is basically 0. So, what we find is that torsion alone does not generate any radial displacement. Okay. If you stretch a beam, then yes, the radial shrinkage is there. So, there will be u r. So, due to epsilon z we have u r, but due to torque there is no deflation or inflation of the cross section. All right. So, what this tells us is that u r is 0, u z is also 0 because epsilon z is not there, but u theta is there. And how much would be u theta? That depends on what is the rotation of the cross section. So, suppose the cross section rotation is omega. So, this becomes omega of z times the radius. So, u theta is simply omega of z times the radius. So, what will be the strain matrix then? The strain matrix becomes very simple. There is no u r. So, epsilon r r is 0. What about epsilon theta theta? So, that is u r by r plus 1 over r times del u theta by del theta. Now, this u theta does not depend on theta. So, epsilon theta theta is also 0, epsilon z z is also 0, and we knew that epsilon r theta and epsilon r z also turn out to be 0, but only epsilon theta z is not equal to 0, and epsilon theta z was equal to half of del u theta over del z plus del u z over del theta into 1 by r, but there is no u z. So, this goes. So, finally, we have simply half of del u theta by del z. So, this is half of del omega by del z into r, and what is del omega by del z? It is the rate of change of angle, right. So, that is the twist. So, this is twist k into r, and this implies that gamma theta z is simply k into r. All right. So, once we got the epsilon matrix, we then have to think about the stress matrix. So, the stress matrix in cylindrical coordinate system, you see that each of the normal strains epsilon r r, theta theta and z z, they are all 0. So, that would mean that sigma r r, sigma theta theta, sigma z z, they would all be 0 too. Can you recall the formula for sigma r r? So, that was lambda times epsilon r r plus epsilon theta theta plus epsilon z z plus 2 mu into epsilon r r. Now, each of these are 0. So, sigma r r becomes 0. Likewise, sigma theta theta, sigma z z, they will all become 0. Okay. And then the strain epsilon r theta is 0. So, sigma r theta also becomes 0, sigma r z also becomes 0, but we only have sigma theta z or tau theta z, right, which is equal to g times gamma theta z. So, this becomes g into the twist k times r, and here is g into the twist k times r. Okay, so, this is the state of stress due to torsion. So, when you have a cylinder and you are only applying torque to it, then the state of stress, the stress matrix will have everything 0 except for tau theta z. All right. So, we can write here, in case of torsion alone, only tau theta z is not equal to 0, but rest all are 0. Okay. So, this is the state of stress for any point in the shaft, and we have to find out the maximum shear component of traction at a point. So, at a point we have so many planes, among all the planes we have to find out what is the maximum shear component of traction. So, how to find that? we have to first get the principal stress components. Suppose we have lambda 1, lambda 2, lambda 3, and lambda 1 is the maximum and lambda 3 is the minimum. Then tau max is lambda 1 minus lambda 3 by 2, that is the maximum value of shear stress, right. Now, with this stress matrix, we would also have to find out the maximum value of shear stress. So, first we have to find out the principal stress components. Now, see that this stress matrix is really in a nice form. The first column is all 0. That means, it is also the principal axis. So, in this case the first column corresponds to E r. So, E r is also the principal axis, but on E theta and E z we have tractions which are not along the normals. So, they are not the principal axis, but since one of the coordinate axis is the principal axis, we can use Mohr circle now, right. So, if we think of using Mohr circle for this state of stress, so we are going to use Mohr circle for theta z plane. So, the normals here are some cos theta times E theta plus sin theta times E z. So, we are looking for planes whose normals are of this form. So, we have to first put the value of sigma theta theta and sigma z z, but they are both 0. Then we have to put the value for tau theta z, and that is at g k times radius, right. So, the center is at the origin itself, because sigma theta theta and sigma z z are both 0. That means, sigma theta theta plus sigma z z by 2 is also 0, which is the center of the Mohr circle. All right. With center known and the theta plane known, we also get the radius. So, this becomes the radius, and then this is your Mohr circle. Okay. And now you can extract. So, this is the maximum principal stress component. So, this becomes your lambda 1, which is also equal to the radius, which in this case is simply g k into r, correct. Likewise, this is minus g k into r. So, this would be lambda 3, the smallest one, and lambda 2 is 0, because we know that one of the principal stress component is 0 here, right. On E r plane, the normal component of traction is 0. So, lambda 2 is now 0. So, what is tau max then? So, tau max is simply lambda 1 minus lambda 3 by 2, which is also equal to g k into r. Okay. So, as per the question, we had to find out the maximum value of shear component of traction, which from our analysis turns out to be g k into r. Okay. So, for a given shaft, so we have 3 shafts here, right. So, we have 3 shafts. Look at the bronze, for example. So, the value is g k into r. So, in bronze, g is the same everywhere. The twist kappa could be changing along the axis, right. We do not know, we have to find out. And then the radius. So, radius is also changing for different points, but on the lateral surface we will have the maximum radius. So, it means that the shear component of traction gets maximized on the lateral surface, because we have maximum radius there. And then we have to find out where is the twist maximum in bronze, in aluminum and in steel. Okay. So, how to find out twist? Okay, but we know that the torque T at the cross section Z, remember we are using Z now, because for the axis we use Z coordinate. So, torque T is equal to G of Z times the twist K of Z into J of Z, right. So, this implies that K of Z is equal to torque of Z divided by G of Z into J of Z. Now, if we concentrate only for the bronze, let us say, then for the bronze everywhere we have the same G and we will have the same J also, because the cross section of the bronze is also the same everywhere. So, this denominator is constant for the 3 shafts. Separately. So, then we have to find out whether the torque is varying for each of the shafts. So, to do that we can draw the free body diagram. So, let us suppose we think of this part of this shaft, where the cut cross section is in the bronze, and similarly we will take for the aluminum, then for the steel. Okay. So, when the cut cross section is bronze, so we have T p, the reaction torque, and T z, because it could be varying and there is nothing else, right. So, when you do the torque balance, this simply tells us that torque in bronze is equal to T p. Very interesting. So, torque in bronze is equal to the reaction torque from the left end. Likewise, let us do the torque balance such that we get the cross section in aluminum as a cut cross section. So, we have again T z, and then we have T 1 at the interface, and we also have T p. So, when you do the torque balance, we get that torque in aluminum is equal to T p minus T 1, is not it? Likewise, when you do the torque balance with still as the cut cross section, so here we have T z, and then here we have T 2, and here we have T 1, and over here we have T p. So, this implies torque in steel is equal to T p minus T 1 minus T 2. So, you see what this tells us is that torque within bronze does not vary. Similarly, torque within aluminum does not vary, and likewise for the steel. This is really interesting. So, if we come back to this formula, then torque is also constant within bronze, G is also constant within bronze, and J is also constant within bronze. So, that means the twist K is constant within the 3 shafts. but of course, this does not tell us that the twist in bronze is equal to twist in aluminum. So, they are not equal, okay. Just like the torque in bronze is not equal to torque in aluminum, is not equal to torque in steel. So, each of the shafts have got their own twist, but it is same within the shaft, all right. But still, how to get the twist? If you want to get the maximum shear, we know it is equal to G times K times R. So, we still have to get K, right, the kappa twist. So, we have single unknown here. We have written down the torque in terms of the reactions for each of bronze, aluminum and steel. So, it is written in terms of the single unknown T p. So, what equation do we use now so that we can obtain T p? So, look at this setup again. The two ends are clamped, right. So, those two ends do not undergo any rotation. Now, look at the bronze. So, the bronze end, the cross section at R, cross section here, it is going to rotate relative to the cross section at P. So, the end to end rotation in bronze will be something. Likewise, end to end rotation in aluminum will be something, and end to end rotation in steel will be something. But when you add all the three, then the total end to end rotation has to be 0, right, because you see the rotation at P and the rotation at Q, they are both 0. So, the end to end rotation for the total setup is 0. So, that is one equation which we can use now. So, you see we are using the deformation of the beam to find out the unknown. Okay. So, omega r minus omega p. So, that is the end to end rotation for bronze. So, this should be equal to torque in bronze into length of the bronze divided by shear modulus of bronze into J of the bronze, correct. So, that is the formula which we derived, because within the bronze everything is constant. So, we can use this formula now, T L by G J, end to end rotation. Okay. Likewise, for aluminum, omega s minus omega r. So, that is the end to end rotation for aluminum, and that is equal to T aluminum into length of aluminum over G of aluminum times J of aluminum. Similarly, the end to end rotation for steel, so that is going to be omega q minus omega s. And this is equal to T s into L s over G s times J s. And when you add all these three together, so adding the three together, we get omega r minus omega p plus omega s minus omega r plus omega q minus omega s. So, this is the total end to end rotation. Can you see it? You see this omega s cancels with this omega s, and this omega r cancels with this omega r, and we have left here omega q minus omega p. which is total end to end rotation, and that we know is equal to 0. So, this means T b L b over G b J b plus T a L a over G a J a plus T s L s over G s J s, that is equal to 0. And now you can plug in the formulas for the torque in each of the 3 shafts, right. So, this means T b is T p into L b over G b J b. For aluminum it is T p minus T 1 into L a over G a J a plus T s is T p minus T 1 minus T 2 into L s over G s J s, and that is equal to 0. So, this implies T p into L b by G b J b plus L a over G a J a plus L s over G s J s, and that is equal to T 1 into L a over G a J a plus T 1 plus T 2 into L s over G s J s. Okay. So, from here you can now compute T p. So, this is going to give us now T p, the reaction. Once you have gotten the reaction, then you get torque in each of the 3 shafts, right. In bronze it is T p, which you just solved for. In aluminum it is T p minus T 1, and T 1 is given because that is something you are applying, and for the steel it is T p minus T 1 minus T 2. So, once you get torque in each of the 3 shafts, then how to get twist? So, twist K. So, we have the formula already written here, you see K is then T by G j, and once you get K, then tau max you can get from this formula, it is G into K into R, and for R you plug in the outer radius because that is the maximum. All right. So, that is about solving shafts problem involving more than one material, and you are doing some torsion. Okay. So, I hope you got some idea about how to solve torsion problems. All right. So, we will continue with our theory then in the next class. Okay. Thank you.